Hi everyone, welcome to another installation of Engineering Hour with David on this Sunday. So me, who am I? I'm Zacck Osiemo, and I'm a software engineer at Zacck, where we build a lot of embedded systems. We're an embedded consultancy basically, but we try and specialize on building embedded systems for government tenders. And today, here's what we're going to cover from today. So we're going to look at how to bring what first of all, what is machine learning and AI, and then we're going to look at how to come up with applications that use machine learning and AI, and then after that we're going to look at how these applications can be edge applications, or rather embedded applications, which is what most of us want to do, and then we're going to look at an overview of integrating this AI artifacts with our applications in embedded. So what to expect from today's session is mostly that this is going to be an overarching session. It's the first in a 4-part series on AI with FreeRTOS. And since we use quite a few tools to achieve AI with FreeRTOS, what we're going to do today is basically get introduced to the tools that we're going to be using and know which ones belong to where, and understand what reference information that we're going to use them, and then how to join all of these tools and all of this knowledge into applications that use AI, and what is it that an AI application is. So, cool. So I'd like to start by let's define, when I was getting into this, the edge or the border between machine learning and AI was quite difficult for me to find or to kind of sense out. So I'd like to sort of spend a little bit of time to define what machine learning is and what AI is and artificial intelligence is, and where do they fall in relation to each other. And once we have that, we can actually speak about things where everyone has context of what we're doing. So, and artificial intelligence is basically artificial intelligence, which is, if you break up the word and you use other words to define that statement, it becomes made up intelligence. What is intelligence? Intelligence is the ability to learn from information, past experiences, and to use this learning on this information and past experiences, to use this learning as context for for making future decisions. So that's what intelligence is. And basically, artificial intelligence is a whole group of fields or sub practices that culminate into made up intelligence. One of the made up intelligences the one that we're going to focus on today is machine learning, which is a subset of artificial intelligence that involves making systems that learn how to perform a task, basically without giving the rules for the task. So whenever you're building a system, that does something. So let's say you're building a system that processes credit cards. Your system will have some rules. Take the credit card from the credit card number from the person. Check if the credit card number has enough credits. Spend the credits that you need, and then report to the person that you spent this much credit. So those are rules. You're giving the system rules in order to perform that task. However, with machine learning, this is now programming a system to perform the task. However, you don't give them the rules. What you give them are successful results, or rather symptoms of a successful result. And they will keep performing the task. And whenever the machine sees that it's performed the task in a way that provides successful results, it will classify that way as a working way. And that is basically what machine learning becomes. It's one of those, you're not exactly using rules, but you have given the system rules to use to build, say, other rules that it can do. And machine learning itself is based on deep learning, which is where systems can learn from patterns that are hidden inside data sets. Or rather, if you collect a lot of information, say you do a lot of credit card processing, or you do a lot of checking of green lights, and you know who's going to cross the line or not. When you have this amount of information and you use this information to make clusters of results, this is a right result and this is a wrong result, that is deep learning. And then that is a smaller part of machine learning. And machine learning itself is a bit smaller part of artificial intelligence. So that's the difference of machine learning and artificial intelligence. High level view, machine learning is a small part, or is one of the ways to achieve artificial intelligence, because there's many ways of doing this so that you can get artificial intelligence. You can do systems based on things like rule-based logic. You can do things based on something like supervised and unsupervised learning. So there's many ways of achieving artificial intelligence, and machine learning is one of them. Okay, so let's look at what ingredients go into coming up with machine learning as a concept, or rather making a thing that does machine learning. So there's a number of different ways. There's supervised machine learning and there's unsupervised machine learning. Supervised machine learning is kind of where you are instructing the machine on how to interpret the data. So you're giving it like example interpretations, and you're wanting it to copy your interpretations. And then unsupervised learning is where you're just collecting a lot of data and you want it to group the data into correct data and bad data. So one of them looks like following instructions, and another one looks like clustering, or rather heat maps. You enclose areas where right examples are and where wrong examples are. And once you enclose those areas and you use those areas as inference to check whether, like, is this something I want or is this something I don't want? So the key concepts when you're implementing a machine learning application, you're going to want to do data collection. You're going to want to collect data of your successful results. You're going to want to collect data of your unsuccessful results, and you're going to want to train something called a model. So a model is a carcass or a caricature of a decision-making structure. When you make a model, you basically create, and I'm oversimplifying here because of the time we have. When you make a model, you basically make a way of making a decision. So the first thing you need to do is collect enough samples of correct decisions and wrong decisions, and teach your model or train your model on this wrong and right decisions so that it can differentiate them. Okay, cool. And then once you have done that, you're going to now, you have a trained model, but you need to do stuff like apply it in the field. So applying it in the field will start by gathering some input. And then once you gather some input, you will clean up the input so that it is understandable by the model. And then you will now use they're called features. You'll now use the information in the input to now make features upon which this model is going to be using for decision making. So later along the line, we'll see how we can use sensor data, something like accelerometers for gestures. So the application that we're going to look at today is going to be gesture recognition using machine learning. And if you think about gesture recognition, so whenever you move, so if you look at my mouse cursor on the slideshow, gesture recognition is to, like, this is a gesture to make the mouse cursor bigger. So what we want to do is to enable gesture recognition so that if someone does this or if someone does this, we still recognize the different movements. This is a smaller one, but it does it, and this is a bigger one, but it gives the same effect. So what you want is for the machine to be able to differentiate those two gestures and determine that they're the same gesture. That's the example that we're going to deal with today. We're going to look at how using sensor data can augment into that so that you come into machine learning. So as I said earlier, you have supervised and unsupervised learning. So in supervised learning, you have classification. It's a classification system. So you are helping the machine determine. You're almost letting the machine determine as far as it can, and then you're helping it define the edge. Like here is defining the edge between the red circles and the blue squares and the green stars. So you'll let the machine try and separate these. And as the machine tries to separate this, the thing you'll do is you'll enforce it by telling, if it puts a square, if it puts a red, a blue cross here, you will move the blue cross into this space. And by doing that, you will show the machine that this was in the wrong place and such. And hence, that becomes your supervision as the person who is doing the machine learning. You're now supervising what the machine learning tool is doing, and you're helping it go further. With clustering, this is, as you see on the other side, which is another type of machine learning, you're basically leaving this all to the machine. You're letting the machine go and check where the red circles are and where the green stars are and where the blue crosses are. And what you're doing is you're letting the machine draw all of these borders and keep them in those edges and let them stay there. And you're basically not helping the machine, and you're trusting it enough to make the correct borders that you want. So that's what unsupervised learning is. Those are the two types of machine learning that are mainly in use in the industry today. Good. So let's look at how machine learning, how once you have this machine learning, you can now do things like collect gestures. So like if you're looking at my mouse again, so I'm shaking my mouse, and my mouse is not becoming big. But if I rapidly shake my mouse becomes huge. So our machine is able to recognize that this gesture, because you can see my mouse is not getting big, and it's not the same as this gesture where my mouse expands big. So the way you do that is you collect enough samples of this gesture that makes the mouse big, and you collect enough samples of this gesture that don't make the mouse big, and you use these samples as input data as input into the training of the model. Not input into the model itself, but input when training the model. So when you're training the model, is you're helping the model do classification. You're helping the model pick what it should listen to and what it should not listen to. Once you've done that, you will have a machine learning model that you will be able to use in your embedded application. And the machine learning model will be able to receive gestures. So gestures in this sense will be, I'm moving my mouse. You will be able to be sent that data using an accelerometer that is in my mouse, or a laser, whatever way they're using to collect that data that I'm moving my mouse. This data will be pre-processed. This is like, we will take all the accelerometer data and see how fast I'm moving, and we'll make a frequency, and we will make it into a shape that the model can understand as this movement. Okay, cool. And then once we do that, we will run TensorFlow Lite, which is one of the tools that we're going to be using. It's the next thing I'm introducing. We'll run an interpreter. The interpreter will now interpret this as an expansion gesture, and then this will use the model. This is this part. So the interpreter will use the data that we use to train the model. You see, the model is trained off the system to train the model, and then it will recognize that, and it will handle the output by telling the machine to make my cursor bigger. So that is how machine learning fits into AI, into embedded applications. So it's supposed to be AI embedded applications, not AI applications. So that's how machine learning enables embedded applications in a context such as this, which is gesture recognition. Sorry. So one of the things we need to consider when we're looking about embedded applications and machine learning is that embedded applications don't traditionally have the capacities of the tools that we usually use for machine learning. If you've been watching any sort of news, and you've realized that whenever they're describing computers that are going to be used for machine learning, basically, whenever they're talking about NVIDIA chips and that NVIDIA is now one of the most expensive companies on earth, is because they make a very specialized, very powerful computer to use for machine learning. And usually, the features that are inside those big GPU machines from NVIDIA that are programmed in like CUDA and such, those features don't fit on small embedded platforms. First of all, our small embedded platforms have very limited power. They have very limited memory, so they can't store large swaths of information. We have, because we have very limited memory and we have very limited power, we don't have that much flexibility in applying privacy and security. So you have to be careful about what kind of inference and what kind of information you're building or you're using from whenever you're working with embedded systems. And then embedded systems tend to be slower, and then they tend to take longer to respond, which is so they're slow. They don't. The CPU isn't that fast, and sometimes they're connected to a very slow network, and sometimes the slow network is not fast enough to ping back responses really quickly. So this is another challenge. And then another thing is, because we have very little resources, how do we make these devices feel like they belong to their owner? Okay. So along with all of these challenges, you realize that applying machine learning, those big models that are used to do machine learning have a lot of input data and a lot of output data. So they're big, both in space and the time they take to run. So this is not the kind of capacities we have in these systems. So we need frameworks that can build lightweight models, that can build models that can fit on small embedded systems and work on battery power and be able to like perform, but at a very starved, at a very small level of resources. And that's where TensorFlow and TensorFlow Lite come through. So TensorFlow Lite is a machine learning platform. It's built by Google, and it's based off of TensorFlow, which is one of their main machine learning platforms. And basically, TensorFlow Lite is minimized. It's made smaller, it's made more performant, and it's made that it can run using microcontroller features better. And it used to be called TensorFlow Lite for microcontrollers, but recently, I think weeks ago, they renamed it to Lite RT. And that is, you basically, what you end up doing is you use the main GPU processing to make your model. So you train your model on a GPU processor, on a big computer, or not an embedded device. Once you have your model and it's doing, it is giving you the results you want, you now convert this model. All you need to do to convert the model is basically making a C array out of it. You basically you make a C array, an array that is compatible with C, and that array can be used by the inference tool, the inference library that TensorFlow Lite provides. So they enable you to make a model into a TensorFlow Lite model, and then TensorFlow Lite provides you an inference library that you can pull into your code, and you can use this to use the model now. You can pull the model into your code using the inference library, and then using the inference library, you can infer on whatever. You can now recognize gestures, basically, is what I'm saying. I'm trying to explain. Okay, cool. So let's look at one of the applications. So the application that we're going to look at today is gesture recognition. So in general, we can do any sort of gesture recognition, and I wanted to leave it in a very general sense, but I wanted to also show an example. Well, one of the first examples I started by showing is I showed it on my screen where I moved my mouse and my mouse started expanding. That is a beginning application. Another few applications are things like where you have drones or something, and you've heard of drone racing, or people who use drones to go and deliver very like sensitive material or do like bomb disposal and stuff of the sort, whenever a drone is being used and they need to use their arm to control the drone and to control the pitch and the yaw and the lean and everything. And that is one a simple application. And then you can have sort of manipulator robots that are inside areas that are unsafe for humans. So you could have something like robots that clean the bottoms of swimming pools, because nuclear reactors are covered using swimming pools. There's always a huge swimming pool on top of a nuclear reactor. And sometimes you send humans to go and clean the floor. Sometimes you need to send, but however, humans, it's quite dangerous to send humans there. So you could have a manipulator robot that goes down into the pool and cleans up the pool and does such kind of actions. And this is where you will need tools like machine learning to recognize gestures such as grabbing, picking up, and whatever you're doing with your hands that you need a computer to recognize and make a robot copy of. Is basically a good application of gesture recognition and in machine learning. Okay, so having looked at that, we now know, I'm going to do a sort of mid-session recap. We now know what machine learning is. We have an idea of what is it that we need. We know we need a machine learning platform for the main sort of platform tools, which in our case is TensorFlow. We know we need a machine learning platform that can be translated into embedded systems. And in our case, that's going to be TensorFlow Lite or TensorFlow or Lite-RT. And then, as obviously, we're going to need some sort of hardware, this piece of unit. In our case, in this series, in this four-part series, we're going to be using an STM32F4. And after that, you just need to start. Remember, we need to collect a lot of data to pump into this learning model so that we can get our model trained so that it can recognize the things that we need to do further. So that is kind of what we've covered so far. And at the tipping point of that, we've looked at how do we apply this? So once you can recognize gestures, where would you use that? And what we have looked at is a few examples that can be used with recognized gestures, or rather you can build it for that. Okay, cool. So now let's try and look at a machine learning application that is based on an embedded system. Now we're finally back on familiar territory. We have an embedded system. I'm assuming we have a machine learning model that has been trained not on an embedded system, on a GPU system, and it's correctly inferring the good results and the bad results, and it can recognize gestures, and it can recognize what is not a gesture, and it can react. And based on that, we can send signals to other subsystems to react as they need. So, and this is where we see, this is now where you start seeing the need of a real-time application. So doing a gesture such as this, you can't always be, because recognizing a gesture such as this, you can't always be on a main loop just trying to register that gesture, because I'm using my mouse, and I can use my mouse to do many things. I can right click, I can left click, I can move my mouse. There's so many other things that I can use my mouse, that you need to be sensitive about other things while you're also recognizing gestures. So now you're entering a realm where there's things that are happening, but they have time deadlines. Like, if I'm doing this gesture, you need to recognize it before I move on to click something else, before I move my mouse to go click something else. So there's some time constraints that are being introduced here. There's like, if I shake my mouse like this within some amount of seconds or some amount of microseconds, please then recognize the gesture. If I just move this mouse and it takes me long to go across the screen, then don't recognize the gesture. So we need a real-time system to be able to help us divide this work and subdivide it in such a way that we can do it in a way that feels responsive and quick to the human. So let's think about the sort of tasks that we're going to have. So as I'm moving the mouse, we obviously will need a task that collects the sensor data. So basically, connecting the accelerometer data on where am I moving the mouse towards the left? Am I moving the mouse towards the right? Am I moving it up? Am I moving it down? So that's we need to be doing that constantly all the time, because I don't want to recognize a gesture and then have my mouse not be able to move down because it's expanded. And then as we are moving our mouse, we need to be collecting this data and processing it and checking it in such a way that, are we doing navigation, or are we doing a gesture that does not mean navigation? So it could be clicking, it could be right clicking, it could be this, it could be some sort of other gesture that does not mean the particular one that we need, or rather this gesture means that, and this gesture means expand. Or this is there you go. I could have my mouse, my floating menu, and at the same time I might need to expand my both. So we have, in essence, we have simultaneously, we need to run two tasks at the same time. Oh, sorry. View slideshow. Please be at the right place. Okay, cool. So what I'm basically implying is we have a lot of work to do, and we need to do it in given times so that we can match the speed at which life happens. So we have a task that collects the sensor data. Is the mouse moving? A task that checks, is this movement data I can use? Was that movement too slow and I need to dump it? Was that movement too fast and I need to recognize it? Was that movement up or down? So we need another task that is preprocessing. And then we need a task that is taking up all the process data given on a certain amount of time, on a certain set period, and it is recognizing that as a mouse expansion, or a left click, or a right click, or a left click while we are expanding the mouse. It's all of these features. And then at the top of that, we also need to show the results. What you realize is the system is recognizing that I'm shaking the mouse, but we also need to show the user that the system is recognizing that is recognizing the gesture we want it to recognize. So we also need to, as this is happening, as quickly as we're recognizing that the mouse is shaking and the cursor needs to be magnified, we also need to recognize that we need to inform the user that we have recognized this gesture. So we should have another task that is constantly sharing, because at this point, if you don't realize, my mouse cursor is expanded, my mouse is recognizing that my mouse cursor is expanded, my mouse is recognizing that I'm expanding, and expanding is happening at the same time. So there's a few things just by the virtue of that mouse being huge and it shaking at the same time. There's a lot of processing that is happening at that time. Cool. So hence we need a real-time system, and in this case we're using FreeRTOS, and this is why we need it. And I've outlined a few tasks that can be seen in the next thing. So in reality, as I've said, what is really happening isn't, we're not just recognizing the mouse and that's all we're doing. In reality, we're taking some time to recognize a feature where sometimes nothing is happening, like right now I'm not moving the mouse, it's idle. And then when I start recognizing, I say, oh, there's a data that we're collecting the sensor tasks, and then I could start moving and stop, it could go idle. And then I could start moving again and then stop and it goes idle. But I could start moving and then suddenly I do a gesture action and it needs to pre-process, and then after that it would, you see, it would recognize the gesture and it would move it. And as I said, we could be, as we are shaking the mouse, it's still expanded and it's still expanding. So we could have more work coming in as we are doing the work that is currently needs to be done. So that's why we need a real-time system, and this is where we need a real-time operating system that is basically swapping around all the tasks and keeping them all running in such a state that we are always achieving what we need to achieve. Okay, so hence, and you can see a good key. Sorry about that. You can see a good key at the top. Task A is sensor data collection, task B is preprocessing, task C is the inference task, and then task D is the output task. As I didn't have enough time to sketch it in, but basically the output task would be showing the mouse as a huge system. Cool. So yeah, later we will cover the same very application in Zephyr if you need us to. We will actually. This is in the process. So basically what we've done so far is we've looked at why we need machine learning, why we need artificial intelligence, and now we are looking at why, after we have machine learning and we're using that in our artificial intelligence application, why do we need a real-time operating system? So we know that machine learning is to recognize the gestures, and then recognition of the gestures takes a lot of separate standalone work. So what we are doing is we're using a real-time operating system to recognize those things. So, and here basically I'm outlining as these steps are. This is a small outline. It's not as it's quite involving. You have to do a lot of work for you to do this. While it's a simple list, it's not a list that you'll cover quickly. So be prepared to do some background work and such. So number one, we wanted to. The first thing you need to do in order to integrate machine learning models into your FreeRTOS applications is you need to train a model. In our case, it's to train a gesture recognition model in TensorFlow, and that will probably comprise of hours of us, being there and giving different signals to TensorFlow and using either supervised or unsupervised learning and classifying this into steps. Sorry. Okay. So train a gesture recognition model, because models are what we use. Once you've trained the gesture recognition model, since we're going to be building this in embedded systems, we want to download the TensorFlow Lite, TensorFlow for microcontrollers library. And when you download that and you want to, you're going to be able. It's going to be probably a C, a header, and a source file, and you will be able to. You'll need to use your build system to integrate this into your application, which is either CMake or whatever system you're using, or STM32, CubeIDE. Since in this case we're building on an STM32, whatever build system you're using, you'll need to integrate the TensorFlow Lite microcontroller library into your application. Then the next step after that, you're going to need to convert the model that you built using the GPU TensorFlow into a Lite model, which is basically a C array. And this is something that you can pull into your application as one of the artifacts that you're going to be using. And then once you've done that, remember you downloaded the library. This library contains TensorFlow Lite interpreter. And this interpreter is something that we can now use to build this is what you will be passing the data through. Remember, when you collect the sensor data that is showing you a gesture, and then you'll pre-process it, which means cleanse it. And then once you pre-processed it and you have the correct amount of data, you will hand over this data into the TensorFlow Lite interpreter, which we're going to look at the second session of AI with FreeRTOS. So once you've collected the gestures and you collected the movement information, and you're handing this information over to the interpreter is going to now do a bit more pre-processing, a bit more validation, and then in there it's going to now start trying to use that data to recognize whether we have a gesture going on or not. And once the interpreter decides whether we have a gesture or not, it's going to now start. We can show us results. Once it shows us these results, we can now start. Basically, the result is the mouse big or is the mouse not big? Basically, it's feeding output. and this will happen in the order of several times a second. And this is where you now go back and realize this is why you need a real-time operating system. And then after you do this, you need to obviously test your application. Test that your application works with shakes with different people. I'm a male, so I shake the mouse a bit harder. My wife would shake it a little less, and it would all like, so you need to collect as many scenarios where you can use as many scenarios where your system can be used. You have to consider whether children are going to be using adults, people or with different cultures, people who stand next to the camera, over the camera, under the camera. So all of this stuff will need to be vigorously done for you to end up with machine learning models that do very well in the field, because they're not, by their nature, they won't be supervised and they'll be doing stuff by themselves. And basically everything you can do, you can only do retroactively. Okay, I think this is more an illustration of why we need the real-time operating system and why we need it specifically in machine learning. So we need it to manage the tasks. Those tasks that are, one is for sensing how the mouse is moving. One is for moving the mouse movement data and putting it in an array or a queue. And another one for taking from the queue and making sure that it's clean enough for the machine learning inference tool. And then running the inference tool and looking at the results from the inference tool and handing that data back into your main thread so that you can show it in another thread in your UI thread. And this is, all of this data is moving. And remember, as we are recognizing a gesture, sometimes another gesture is coming in, or we're already late and we are out of sequence and we're basically catching up to what is happening in the continuous realm of world. So that was just, this one is just an illustration. Cool. So we have 3 sessions coming up next. So, and these sessions are now going to be code heavy. This is the point at which in my presentations, I usually jump into some code and I rush you through some code and I show you some things that are working. What I want to do now is build upon this, and we can have questions here and we can discuss what we've just learned. And then based on that, we can now tackle code in those standalone sessions so that we can understand, because there's going to be when we're training the model, we're going to be looking at mostly Python. And then when we're using the model, we are going to be looking at things like C and C libraries. And the challenges are going to be things like our builders and our building packages and such. So it would be quite beneficial if we tackled all these sessions one by one, because I don't want to jump into a Python session and then we train a model. And then after that, we straight jump into a C session and it gets confusing and the delivery is too much. And as always, our sessions are always meant to give you the best you can from there. So our 3 next sessions are going to be, the next one, we're going to be doing gesture recognition pipelines. How you train, how do you deploy, how do you minimize, how do you convert it into a light model? How do you take the results from the light model and go change the features of the heavy model so that it improves? And then after that, we're going to now work into the embedded section of this part where we're collecting the sensor data from the application, or rather from the sensors on the board or on the on our motherboard, and how we're going to feed that sensor data into the machine learning model that we had from the previous step. And how does that machine learning model reply to our going on information, and how do we use that replied information in our application? How do we deploy that as our application? And then in the final series, we'll look at the challenges that one would usually face in edge AI and the future, and kind of what we'll look at a few samples of what people are doing with edge AI, how people are deploying it, how people are building it up, and basically look at the context of what we have just built and how other people are using it, and kind of entertain what is possible, what is the future, because that's always a good thing to discuss with AI. I feel like I've rambled quite a bit. And basically what I want to do is show you that in this session, what we've looked at is what is machine learning and what is AI. how do we use it in building sample gesture recognition application? What will we do? What will we need to do to optimize that sample gesture recognition system so that it can run on embedded systems rather than big GPU or microprocessor systems, microcontroller systems, basically? And then, basically, after we have the model, can we use sensors to augment the model so that it can decide much better? So that's what we've looked at today, and this is what we'll look in the upcoming sessions. So I think I'm going to take a sip of my tea and then we can cover some questions. I see quite a few of them on the chat. Please start bringing them in. And if there's anyone who wants to join the stage and ask some questions, I think Ashraf was a bit earlier. Let's do it. Cool. Yeah, let's start. Questions.
Nice job, Zacck. So yeah, like Zacck said, if you guys have any questions, please drop them into the chat on whichever platform you're in. Obviously, John asked if there's going to be a session using Zephyr, and Zacck already said yes, we'll do this again or something similar. In Zephyr, there's a question here. Mesh is asking, where do you get the TensorFlow for microcontrollers library? Did you just pull the one that was on GitHub
Yeah. And also, so the next slide, maybe this was a mistake by me. The next slide has a link to a repo that is going to follow all of this work. And basically that repo has all the links that you need. But basically the library is available and you can download it. You can download it by just Googling TensorFlow Lite or rather TensorFlow. It will take you to the same people. It's provided by Google. It is provided by Google on GitHub. So it's not from ST, it's a Google library. Yeah, and yeah, John, on Zephyr, we will cover the same application on Zephyr as well, so that you have relations from both and see how much tasks it is for either. I see Ashraf is on. You have a question, Ashraf?
Okay, so I figure out on interesting thing. Let me share it with you. In previous engineering hour, we watch about PID control, who is take feedback from the previous error, and it do something like this. And if we implement the same kind of thing with machine learning, that becomes AI, right? Like, I mean, kind of.
Well, it does become so. You've oversimplified it, because in machine learning, there's a lot more steps. There's a lot more. You see those feedback loops that we have in AI, in PID that we looked at last week. You see there was like one feedback loop. There was one input, and then from that input, we would just make one feedback loop and it would go again. So the difference is, imagine having 6 PID or 7 PID controllers in a row. And then each one would tune for something else, but the result from the last is going to the next one and the next one and the next one and the next one and the next one. And this is an oversimplification, but that becomes basically something called a neural network. So it's a lot of stuff is built on feedback loops. Get something.
It's kind of data set. The larger the data set is, like the more we can take from it.
Yes. The bigger the data set, the more you can infer from. Remember what we said. What is intelligence? Intelligence is the ability to learn and use this information for future decision making. Just intelligence in itself. So if you can combine as many of these feedback systems, you're basically constructing intelligence. Any other questions or any other questions?
No. I got it.
Okay. I'm bouncing back and forth between different platforms. Anybody have any questions they want to ask by fingers or by mouth? Type them in, or if you're in the event platform and you want to jump on the stage, you can just either request to jump on, or if you have permissions already, just feel free to raise your hand and we'll let you on. I am putting in the links to the Zacck Peter saying that the the dev heads gesture repo doesn't work. Let me make sure that that's gestures with
it depends on what they're trying to do. So at the moment, it's just a place to go. We have not uploaded because look, we have to do this in order. If we just go and upload everything, then it's confusing because you're looking at all of the thing at once, which again results in the current problem with AI, because the current AI applications are you're given something that already works, and then you have to figure it out backwards. So our repo right now is only going to have the steps that we're going to follow. And as we add each step, we will add, as we do each step in public, we'll add it there so that you're able to learn along with this rather than us just dumping a machine learning. You can always just go copy any machine learning application you want if you want, but that's not the point of the DevEd's demos and our engineering hours.
Cool. Dropping in places to go to sign up for the next event. So you can either go to the virtual event platform, or you can go into the Discord event page and you can jump in and indicate that you want to get a notification for the next event. That's a good way to not have to worry about it and make it our problem, not your problem. Anybody else have any questions? Any background, any things that you want to know as we start jumping into this? I think the intention here from Zacck is that we create something that is sort of a collaborative effort, where everybody can participate together. Zacck, I don't know if maybe the repo has, Carla's saying that there's a 404 error page.
Yeah, I just clicked it.
Yeah.
Well,
maybe it's
this. I'm going to share this on the Discord. So,
okay.
Or I'll even put it here on our, I think it's here already. Let me click it from there. Yeah, it should work. The one on the chat right now. So thank you so much. Thank you, Carla. Thank you guys for finding the problems with the link. I probably mistyped something. Sorry.
I think we'll just go back and make sure that there are the appropriate permissions needed for everybody for that repo. But other than that, like Zacck referred, there is a Discord server. If you're in the Discord server, I don't need to send this to you, but if you're not and this is your first time here, check out the DevEd's Discord server. You can jump in there. We'll share the link here to the repo if for some reason you're not able to get it, and we'll make sure to upload the notes from this call there as well. Anybody have anything else? Osterful, anything in addition? Anybody in the audience have any stuff that they want to ask or get clarified for them?
Yeah. And you can also ask about the whole of the past presentation, so we can clarify if you did not understand something.
Perfect.
Yeah.
All right. Well, it seems like that may be it for today. Zacck and I are going to go, and obviously he said that there are multiple sessions after this one, 3 more. So we've got the first one out in a couple of weeks, and then we'll continue adding the 3rd and 4th ones as scheduling allows. And other than that, we really thank you for your guys' time. There's another ping here in the chat, another couple things. Yep, there are a couple of thank yous, and thank you guys. Really appreciate it and love spending an hour every Sunday with you guys, and hopefully we will see you in the Discord server. Thanks a lot, Zacck. Good stuff as always.
Yes. Thank you. Thank you so much, everyone, for coming, and let's hear any topics that you want to see. Thank you so much. Cheers.
Yep. Have a good weekend, everyone.